Okay,
Good.
so I'll just go on with it. So I'll first start by thanking the organizers for giving me this opportunity. So my name is Jéremie Klinger. I'm currently a postdoc in the Rodskov group at Stanford Chemistry. And today I'd like to talk about some of our recent results on trade-offs between energy, speed, and accuracy in driven non-equilibrium systems. So just to give a bit of high-level context, the general question in non-equilibrium control problems is to design a controller, here B, to drive some system X from a source to a target distribution in a finite time that we'll call T total. And we want to minimize the energy cost associated to the driving, as Kai actually mentioned. So there's various definitions and conventions to evaluate the energy cost, and I'll just here stick to the overdamped Langevin paradigm, for which the energy costs of driving or dissipation is given by the total entropy production that will be evaluated as a Strutanovich integral along the trajectory. So in that case, I guess the most general question is, are there constraints on the dissipation associated to the driving? And essentially, how does it depend on the discrepancy between the source, rho zero, and the target rho star? And how does it depend on the total driving time that's allowed to bring your system from one to the other? So actually, part of the answer is already given by a fruitful connection between stochastic thermodynamics and optimal transport theory. And more specifically, so this is a general result that many of you may know, but the thermodynamic speed limit shows that the dissipation, delta S dot, is lower bounded by the Wasserstein distance between rho zero and rho star divided by the total driving time. So just to decompose that formula a bit, it just says that the farthest apart your two distributions in that Wasserstein metric, which is an optimal transport measure of distance, and the shortest, the fastest you want to drive your stem from rho zero to rho star, the higher the energy cost associated to that driving. So it doesn't really matter for us what the definition of Wasserstein 2 distance is here. The only thing that matters is that essentially using optimal transport tools, which are not associated to stochastic thermodynamics, one can obtain numerical evaluation of that right-hand side here and obtain a clear lower bounds on the dissipation. So that's a great result, but one of its key assumptions is that essentially your system has to reach rho star after the total time driving rho theta, and in more than many cases, so most of the cases actually, because you don't have perfect control over your system, over every degree of freedom, for instance, the distribution of your system after T total will not be equal to rho star. And that raises two important questions, which I'd like to address today. So first question is, can we quantify these trade-offs that appear between the dissipation, the total driving time, and the inaccuracy generated by non-perfect controllers? And maybe the second question, can we leverage dynamical optimal transport tools to design these minimally dissipative controllers? So the answer to the first question actually comes from the geometric optimal transport interpretation of dissipation. So you have to think of your system as evolving in that optimal transport Wasserstein space. And essentially, the dissipation is related somewhat to the Wasserstein distance that is traveled by your system when you bring it from rho zero to rho star. So if you want to dissipate the minimal, you actually have to take the shortest path in that Wasserstein distance, here in blue, from rho zero to rho star, that we will call the Wasserstein geodesic. Now, if your controller is slightly inaccurate, you might deviate from this path. So here, say the purple line. And so you might have shorter or longer Wasserstein distances, and hence increase or decrease the associated dissipation. So to quantify properly these trade-offs, what we do is we introduce a notion of proximity in the Wasserstein space. So essentially, we denote epsilon here, the distance between wherever you get, rho t tot, to your target rho star. And then using the metric properties of the Wasserstein space, what we obtain is a bound, which is called the energy speed accuracy bound, that now lower bounds the dissipation associated to such inaccurate driving as a function of still the Wasserstein distance between source and target, the total driving time, so as expected, somewhat. And we also take into account the proximity or accuracy, so how good you did at reaching rho star via this epsilon parameter here. So that's our, let's say, ESA bound result. And maybe three comments on that. So first off, if epsilon is equal to 0, so essentially we reach exactly rho star we recover the thermodynamic speed limit, which is expected. And then second point, again, all the right-hand side parts here can be evaluated, at least numerically, from system samples, say, using optimal transport tools. And then maybe the most important point of that formula is that it constrains the maximum energetic margins that are allowed by inaccuracy. So what this means is that, say, you don't want to drive your system all the way to rho star, there is only so much energy you can spare to do that, and that's given by that bound here. Okay, so to give one concrete example, maybe, just bring that here. Okay, we consider this easy one-dimensional example of a single particle initially at equilibrium with a harmonic trap, and then we start linearly displacing that trap towards a new location. So as we do that, the particle follows, but there is a small lag that develops, and so the distribution of the particle at all times is not equal to the equilibrium distribution with the trap. And so just because that's a one-dimensional Ornstein-Uhlenbeck process, we can compute every single thing in that system. So essentially the instantaneous distribution of your particle at all times. And so we can have access to the exact dissipation, thermodynamic speed limit, as well as the energy speed accuracy bound. So if we look at that picture here, in purple, you have the true dissipation. And what we see is that at all times, the ESA bound lower bounds the dissipation as expected, but the thermodynamic speed limit is just systematically off the track. And that's exactly because there is never a point in time where your system is equilibrated with the equilibrium measure, at least at finite time. Okay, so we've seen that optimal transport theory allows us to provide lower bounds on the dissipation, even in the case of inaccurate driving. And I would like to further that connection and try to see if we can exploit these tools to actually design accurate and minimally dissipative controllers. Okay, so we know that we have to stay on that Wasserstein geodesic, the blue line here, if we want to be minimally dissipative. And that might seem like a very hard task, especially in high dimensional settings. But it just so happens that some recent progress in the machine learning generative modeling community allow us to tackle that issue. So specifically what we do is we're going to leverage a new framework, which is called optimal transport flow matching, that in the paradigm of generative modeling learns a transport ODE to bridge distributions. So for instance, rho 0 and rho star along that Wasserstein geodesic. So all that's left for us to do here is to translate that OTFM ODE framework into an SDE one to match the stochastic thermodynamics paradigm. And doing that, essentially, we can produce ideal controllers. So here there's V and a few comments. So at this time, tailoring the perfect V requires to know exactly all the interaction and forces that are imposed upon the system. But essentially, we have explicit objectives for that control term that can be learned on uncontrolled trajectory data, so say just system samples. And again, because of course real physical controllers cannot be as expressive as these idealized here neural networks in practice, it's good to keep in mind that we have a way to quantify the bounds on dissipation induced by some errors in the driving. Okay, I think I'll just wrap up with two examples. So in this first example, we're driving a single particle initially distributed as a bimodal distribution in 2D to another bimodal distribution in 2D. And we use two controllers here. So in blue, you have the optimal transport flow matching controller, whilst in green, you have just another controller. And what you see is that even if both controllers perform seemingly well enough in the task of reaching that final distribution, when you look at the associated dissipation, of course, the OTFM1 here in blue performs much better and is actually nearly optimal. And so maybe a bit of a higher dimensional example, we look at a cloud of interacting particle in 1D. So these are of the quorum sensing type of, and we put them in some bistable potential and want to drive them from one of the metastable wells here at 20 to the other one at 70 as a group. And so that's a high dimensional transport problem. And again, we simply apply that optimal transport flow matching procedure and monitor the dissipation along the driving. And we see that in that case, we're saturating the ESA bound at all times. Okay, I think I'm done with that. So I'll thank you and be ready for questions.